Hi, my name is Ashen Whitfield, and this is my video lab report for Physics 2211 Lab Experiment 5, the Human Rocket. First, we'll begin with our lab introduction and background info. Our lab overview and purpose. The experimental setup for this lab was that Felix Baumgartner achieved the world's highest skydive, as seen here, in the description below as well. Purpose of the lab is to analyze the motion of Felix Baumgartner during the world's highest skydive, to create a model that accurately predicts Baumgartner's motion, and to compare our computational model with real life. And a brief preview of our results is the model's largest velocity exceeded Baumgartner's true largest velocity, and the computational model mirrored Baumgartner's motion quite well. Physics principles. One assumption that we'll be making is that the acceleration due to gravity is constant at 9.8 meters per second squared. This will be explained in the possible sources of error section. Now on to our principles and formulas. Our first formula is that the force of drag is equal to the negative proportionality constant times the velocity squared in the v-hat direction. Our second principle is Newton's second law of motion, which states that the net force is equal to the change in momentum over the change in time. Our momentum formula, mass times velocity, and our velocity and position update formula is seen on the bottom of that list. Our next physics principle is a demonstration of the effect of drag. First, we can see our drag when dropped from rest. This is before the object has begun moving and begun facing any air resistance, as the only vector is the gravity vector in the downward direction. Next is when the object is accelerating towards its terminal velocity, with the gravity vector being larger than the vector due to the force of drag. And the last model is when the object is at terminal velocity, with balanced force of drag and force of gravity. Next, onto our model information and showcase. We can define our system as Baumgartner and his suit, and the surroundings as everything else, including the Earth and the atmosphere. The mass of Baumgartner and his suit was 118 kilograms. His initial height was 38,969.41152 meters in the y direction. His initial time was 0 seconds. His acceleration due to gravity was 9.8 meters per second squared, which is simplified for modeling purposes, and his proportionality constant for the first time step, which is when he was in free fall, was 0.007219. Our first while loop is for when Baumgartner was in free fall. His force formulas can be seen in the model. The position and velocity update formulas can be seen in the model. Time progression and visualization can also be seen in the model. This is the while loop for our second time step, which is when Baumgartner has opened his parachute. We can see that the proportionality constant is much larger, accounting for the larger surface area of the parachute, causing a larger drag force. We can see the update formulas, time update, and visualization are the same in this while loop. Now onto our results. For our position versus time graph on the left, we can see that his position is decreasing rapidly while he's in free fall, and then decreases at a slower rate for when he has pulled his parachute. The decrease in position is also more linear when he's pulled his parachute. For the velocity versus time graph, when he's in free fall, he's rapidly approaching his terminal velocity, and as he approaches that, he suddenly pulls his parachute, causing rapid upward acceleration after his parachute opens, increasing his drag. This leads to his new terminal velocity with his parachute engaged. Results discussion. Comparing the model and the experiment. The model allowed Baumgartner to break the sound barrier, 343 meters per second, at about 16,500 meters above the surface of the Earth, with his terminal velocity being at about negative 380 meters per second. The experiment also allowed Baumgartner to break the sound barrier, with his terminal velocity being negative 377 meters per second. The model predicted Baumgartner's terminal velocity and motion quite well by this metric. Sources of error include a simplified drag model due to a lack of my coding knowledge to implement a more accurate one. And a result of this, in reality, there's a changing air density due to travel through the atmosphere, and a constantly changing drag coefficient due to the constantly changing air density that could present a source of error. And there's also that non-constant acceleration due to the gravitational force in reality due to a changing distance between Baumgartner and the surface of the Earth. Next, on to our conclusions. Why did this happen? Why do we see aberrations in Baumgartner's actual motion, as seen in the graph to the right? The aberrations in Baumgartner's actual motion can be attributed to the fact that he was traveling through different levels of the atmosphere, and the different conditions faced in each layer of the atmosphere that caused differing drag, including temperature, wind speeds, and more. What does it mean? How would higher temperatures affect the speed of sound? Molecules at higher temperatures vibrate at higher frequencies and allow sound waves to travel more quickly than in environments with lower temperatures. Thus, in an atmosphere with a higher temperature, Baumgartner would have to achieve a higher downward speed to break the sound barrier. We can see in the figure to the right that as temperature increases, so does the speed of sound, and vice versa. Thank you for watching.